Hi, my name is Terry Brown. Welcome to this lecture video for Introduction to Mechanical and Mechatronic Engineering. In this video lecture we're going to look at a design application where we look at torque and rotation transmission, and we'll look at some components and do some calculations. For students at UTS studying this subject, these PowerPoint slides are available as PDFs on UTS Online. Okay, so some of the things we're going to look at: firstly gears, then look at rotational motion in general and how that applies to looking at gears and velocity and torque ratios, and we'll look at belts and chain drives. So just to get us started, I found this little GIF on Giphy, and yeah, it just shows you something a little bit different. Lots of gears all interacting. So we're going to be looking at how we design transmission components just at a very basic level, how we transmit torque and rotation. So starting with gears. So usually we use gears to transmit rotation and torque between shafts. So for example, we might have a shaft here coming out of a motor that's rotating with some speed and torque, and usually when we're using a motor we'll want to decrease the speed and increase the torque. Okay, so we get that transmission and change of speed and torque occurring through the gears. Usually highly efficient if they're well made gears, so you can get up to and even a bit more than 90% efficiency, and we'll look at efficiency later on in the video. They produce a synchronous drive, so you have an exact ratio between the input here and our output. They're usually torsionally stiff and smooth, which means there's no twisting or flexing in the gears. They can be external. Okay, so the gear teeth are on the outer circumference of the gears, or they can be internal like this in the planetary gear set. Okay, so looking at gears, if we think about this thing that we call the pitch circle, which is the locus of the gear contact point. So you can see here we've got our gears coming into contact with each other, and there's a contact point. We have a circle on the input, which is often referred to as the pinion, and then the output, which is the gear. You can see that there's this pitch circle that runs through the teeth. And we can make an analogy to cylinders with diameter equal to this pitch circle diameter, and those cylinders we imagine would be rolling on each other without any slipping. Okay, so this is what we imagine is happening at the pitch circle. These cylinders are rolling on each other without any slipping. So once we do that, we can look at our basic rotational motion. So you should have seen equations like this at high school, or if not in physical modelling at uni. So if we take a point here, if that is at a distance r, and it moves through this distance here, delta theta, or this arc length ds, delta s, then our velocity is the distance ds over dt here. This arc length ds is equal to the radius times delta theta, so we have r delta theta over delta t, and delta theta over delta t is our rotational velocity. Okay, so we'll make use of that in looking at our gears. Okay, so with rotational motion you should be familiar with converting between units, so RPM, revolutions per minute, revolutions per second, degrees per second, and radians per second, and you've got all the conversion factors here. So let's have a quick look at an example. So 1 complete revolution equals 360 degrees equals 2 pi radians. So if we have 1440 RPM, which is a common electric motor speed, what's that in radians per second? So if we put 1440 revolutions per minute, we have 2 pi radians per revolution and 60 seconds per minute. So we can cancel out revolutions here, and we can cancel out the minutes. So we have 1440 times 2 pi radians divided by 60 seconds gives us 151 radians per second. Right, or if you go up here, 1 RPM equals 0.1407. So if you did 0.1047 times 1440, you should get 151 here. So looking at gears now, and if we again imagining that these two things are rolling on each other without slipping, so gears like this, or if you like, let's go to a quick SolidWorks model. Here it is. Okay, so just got a little SolidWorks model here to show you. So if I grab that, I can rotate this. So for that rotation to be transmitted and for these gear teeth to be meshing here, then we need the linear speed of a point on the gear here to be moving at the same speed on same instantaneous linear speed on both gears. Okay, so let's go back to our PowerPoint. Alright, so we saw this before, V equals R omega. So for the two gears, if we have R1 and R2, gear 1 has radius R1 and speed R1, gear 2 has radius 2 and speed 2. And if we rearrange that equation, we get the output speed. So if this is gear 2 here, that's equal to the input speed times the radius of gear 1 over the radius of gear 2. Okay, and we can apply this relationship to tooth belts and chains also, which we'll be looking at later. Okay, so taking that further, so just carrying that relationship that we just found here, looking at the velocity ratio. So you'll see reference to velocity ratio for gear sets, also torque ratio that we'll look at later. So the velocity ratio is simply the output speed over the input speed. Okay, and then using our relationship that we had here, we can do some more rearrangement. Velocity ratio, output speed over input speed, or the rotational speed of the driven gear. So we talk about the output as the driven and the input as the driving gear. Okay, so our velocity ratio then becomes the driving gear radius over the driven gear radius. Okay, you can see these swap over here because this is V over R2 on the top. Okay, so since the number of teeth n must be proportional to the radius or the diameter of the gears for the same size teeth on both gears, okay, so that in order to have our meshing, so if we go back to our SolidWorks, right, to get this meshing to occur, right, obviously these teeth must be the same size, and so they must be proportional to the radius or diameter for the teeth. So we can put all that together and we can get our velocity ratio and have our velocity ratio equal to the different ratios of output rotation, output speed, and radius of the gear, diameter of the gear, and the number of the teeth on the gear. So we can use all of that also to write expressions for the output speed of the gear relative to the input speed of the gear based on the radius of the gear, diameter of the gear, and the number of teeth on the gears. Okay, so I've just carried that across. So looking at these equations, if we want to decrease the speed from one shaft to another, we go from a small gear with fewer teeth to a larger gear with more teeth. Okay, so if we just go back again to our model here, so you can see that gear 1 goes around once and gear 2 has only gone around half. Okay, so if we go around a bit more, go around twice on gear 1. Gear 1 has gone around twice for gear 2 to go around once. And of course we can go the other way. To increase the speed, then we go the opposite way. We start with a larger gear and we go to a smaller gear. Okay, so we can put gears together in a gear train like this. So we can have gear 1 here with n1 number of teeth and omega 1 speed connected to a second gear, connected to a third gear, connected to a fourth gear. So for a simple gear train, it's a serial chain. So each shaft carries just a single gear on its shaft. Okay, so what you may not realize is that all of these, or these two intermediate gears here, do not alter the output over input ratio. So if we simply took these away, so if we got rid of that and move this into here to be in contact, the output over input ratio would be exactly the same. Okay, so these intermediate gears here simply allow us to separate the input from the output. So let's go and have a look at the at a SolidWorks model of that. Okay, so if we look at this simple gear train here, right, and we'll move the input, right, the output of this gear 4 will be the same if we had it move this gear 4 here up against gear 1. Okay, a little bit hard to see that just visually, so let's go back to the PowerPoint and just do a calculation just to show that. So if you put some numbers on these things, so gear 1 has 20 teeth, gear 2 has 40 teeth, gear 3 has 15 teeth, and gear 4 has 35 teeth. So we just use our simple gear speed relationship equation. So output, or gear 2, is equal to the input speed, gear 1, times the ratio of the number of teeth that we saw before. Output gear 2 is equal to input speed of gear 1 times the ratio of the numbers of teeth. Alright, so then if we look at the ratio going from gear 2 to gear 3, okay, so we talk about driving and driven gears. So gear 2 here is driven on this side, but is driving gear 3. Okay, gear 3 is driven on this side and then is driving gear 4, and then gear 4 is a driven gear. Okay, but let's have a look at the equation for going from gear 2 to gear 3. Alright, so the output speed of gear 3 is equal to input speed of gear 2 times the ratio of the numbers of teeth, so N2 over N3. But we can then substitute this up here down into that, so that we end up with omega 3, or speed 3, is equal to the input speed 1 times this ratio of gear 1 over gear 2 and gear 2 over gear 3, and of course we can see that that will cancel with that. Okay, so we're left with the speed of gear 3 equals the speed of gear 1 times N1 over N3. Alright, so already you can see that the equation for the ratio of speed of gear 3 to speed of gear 1 is that same ratio of just the gear teeth. Okay, so we've got N1 over N3, so it's as if this N2 doesn't exist in terms of the speed change. Alright, so if we go to the next one, looking at gear 4, the speed of gear 4 is equal to the speed of gear 3 times the ratio N3 over N4. But again, we can take this, substitute it into here, so then that becomes speed 4 is equal to speed of gear 1 times this product of the gear teeth ratios, and again we can see N3 and N3 cancel, so we're just left with speed of gear 4 is equal to the speed of gear 1 times the ratio of their numbers of teeth, so N1 over N4. Okay, so again exactly the same as if gear 2 and gear 3 didn't exist and gear 1 and 4 were directly contacting each other. Okay, so that comes down to 20 over 35. Alright, so the next type of gear train is the compound gear train. So here in this case we use this for when we want to have a large change in speed and or torque, and also if we want to make the gearbox physically compact, so we want to make it small. Okay, so we don't want to have one small gear to one really big gear, and even just doing that, even if we could fit it, is not very efficient. Okay, so we make use of this compound gear train, and in a compound gear train there's more than one gear on each intermediate shaft. So here's our input here, here's our output, input, output, and this is the intermediate shaft, and in this case gear 2 and gear 3 are rigidly connected together, so they rotate at the same speed. Okay, so in this case the intermediate gears will influence the velocity ratio. We'll do a calculation for that, but before we do, let's go and have a look at SolidWorks again, and we'll look at the compound gear train, not that one. Okay, so now I've got a compound gear train. As I rotate gear 1 here, gear 2 rotates, and gear 2 and 3 rotate at the same speed because they're keyed together here, and then gear 4 rotates much more slowly. Okay. Alright, so let's look at that from front view. Alright, so you can see that gear 2 and 3 rotate together at the same speed. Okay, you see that? Gear 2 and 3 are rotating rigidly together at the same speed, so that will influence the speed relationship between output gear 4 and input gear 1. Alright, so let's go back to our PowerPoint. So here we've got the same compound gear train, same numbers of teeth as we saw previously for the simple gear train. So let's start doing the calculation again. Firstly, we've got input is the driving gear, and this time gear 3 is just a driving gear. Okay, gear 2 is driven by gear 1, and gear 4 is driven by gear 3. Okay, so same again, gear 2 equals, or gear speed 2 equals gear speed 1 times n1 over n2, which we know. Now we note that gear 2 and gear 3 are rigidly connected together and rotate at the same speed, so we can write omega 3 equals omega 2. And then we again use our ratio equation. So gear speed 4 is equal to gear speed 3. So this is our gear connection here, and the ratio of the speeds is n3 over n4. Okay, as we've seen previously. Alright, so we can substitute that into here, and then we can substitute this into here. Right, and then omega 3 is equal to that, so we can then substitute that into here. Okay, so if we do that, we end up with gear speed 4 is equal to gear speed 1 times n1 over n2, our ratio here, and then n3 over n4, our ratio at our other gear connection. Okay, so now we end up with a much greater change in speed. Okay, so here we're 3/14 of the speed of gear 1 at gear 4. Okay, so previously for the simple gear train we had 20 over 35. So now we've got 20 over 35 times 15 over 40. Okay, so this is everything that we've just done previously is all summarized in these next few slides for you. So I'm not going to read through all these again, they're just there for you as a summary of what we've just looked at. Okay, so now looking at torque. Okay, so now in order to look at torque, we're going to imagine that we've separated the gears and look at the contact force between the two gears. Alright, so in this diagram here, I've shown the force as tangential. I've only shown the tangential force. The actual contact force is at about 20 degrees to the pitch circle diameter, so the actual contact force is here, like this. What I haven't shown on each diagram is the horizontal component in this direction. Okay. Alright, so this is normally that 20 degrees here. Okay, but we're just going to look at the tangential components. So we've got input speed, output speed, input torque or pinion torque, and output torque. So let's go and have a look over here in a bit more detail. Alright, so we know from our moment equation that torque is equal to the radius times the force. So here we've got our force, radius of rp, so the torque is equal to rp times this force, tangential contact force. On the gear, we have the gear torque equal to the radius of the output gear times the same tangential force. Okay, because from Newton's third law we have equal and opposite action and reaction. Alright, so we can rearrange this equation. So the tangential contact force is Tp over Rp, pinion torque over pinion radius, which is also equal to the gear torque over the gear radius. Okay, so we can rearrange this so that we have the gear torque equal to the pinion torque times the ratio of the gear and pinion radii. And as we've seen before, the numbers of teeth must be proportional to the radius or diameter of the gears, so we can have the ratio of the numbers of gear teeth to give us the ratio between the torque on the gear and the torque on the pinion. Note that the torque on the input and the output is in the same direction. Okay, so it's opposite to what you see with the rotation. and the speed. Okay, so our torque ratio is output torque over input torque, and we can go through substituting these values into here to get those ratios again. Right, you can compare that with the velocity ratios. Okay, so you can see that for the torque ratio, the radii and numbers of teeth ratio is inverted. Okay, so the summary of our torque equations. So to increase torque and at the same time decrease speed, we go from a small gear with fewer teeth to a larger gear with more teeth. And conversely, to decrease the torque and at the same time increase the speed, we go from a large gear with more teeth to a smaller gear with fewer teeth. Okay, and summary of all that is on these slides here. Okay, so compound gear train summary. Okay, so now we'll extend our look at transmission components to belt and chain drives. So if we start off with our analogy where we had two cylinders rolling against each other without slipping, if we add teeth, then we have our gear drive. If we move the gears apart and then connect them with a chain, then we have a chain and sprocket drive. Or if we come back up here to our wheel drive and move the wheels apart and then connect them with a belt drive, then we're enabling similar torque and rotation transmission. Okay, so if we consider the fact that things can slip, right, so here if in the real world friction transmission like this, it can slip. If we move down here to a belt drive, the transmission is occurring via friction, and there is the possibility of slipping here. That's why we call this non-synchronous drive, because there is a possibility of slipping. We can't guarantee that we have an exact ratio between the input and output. There may be some slipping between the two parts of the transmission system. Whereas when we have a gear drive or chain and sprocket drive, or a toothed belt on a sprocket, then we have an exact ratio between the input and output. We don't have any slipping occurring. So this is known as a synchronous drive. Okay, so here, as I said, relies on friction. The belts or wheels may slip, and precise angular alignment between the input and the output may not be maintained. Whereas over here we have transmission relies on mechanical interaction. The gears or chains shouldn't slip, and we have a precise angular alignment between input and output. With flexible belts, we can do some things like this, where we cross over the belts, so we have the output in the opposite direction to the input, same as with we had with gears. Right, so with a belt and pulley system like this, we have the input and the output rotating in the same direction. Okay, which was not what we had with gears. In two gears connected together, they rotated in opposite directions. The other thing you can do with belts is to twist them like this, so we can change the orientation of the input and output shaft. If we have a tooth belt and chain drive, then of course the input and output still rotate in the same direction. We can't really twist these, and we can make use of our input and output torque and rotation equations that we had for gears and apply them to belt and chain drives. Okay, so now let's have a look at work and power. So you probably remember from high school or physics here at uni that work for a constant force is equal to the force times the distance that the force moves through. For rotational work, have a similar equation where the work done is equal to the torque times the rotation. Again, this is if the torque is constant. If force or torque is not constant, then you need to go back to the integral form of this equation. Power is equal to work over time. So if we now put time into these equations up here, we can see that the power equals force times distance moved divided by the time it takes to move. So the instantaneous power is force times velocity. And for rotational power and work, have a similar equation. Power equals the torque times the rotational speed. Okay, in machinery applications, power is expressed in units of kilowatts. So if we look at power transmitted through a gear train, we have power out equals the torque out times the output speed, and we know that the output speed is equal to the input speed times the gear ratio, and we also have that output speed is equal to the input torque times the inverse of the gear ratio. So we can see here this cancels out with this, and this cancels out with this, so we're left with output torque times the output rotation is equal to the input torque times the input rotational speed. So P out equals P in. Okay, so we can't gain any power by using a gear train. Okay, the power out is equal to the power in an ideal system, and in fact, of course, it's worse than that. In real machines, power is lost through mechanical losses, such as through friction. So we have an efficiency term here in the equation. So the power output is equal to the input power times some efficiency, which is less than 1. Okay, so that's the equation there, where this symbol here represents the efficiency. Okay, so that's pretty much it for the video lecture. There's more information in the following slides. The list of what's there is here for you. So some more tables of symbols for the different quantities in power transmission, some equations. I've just crossed out this one, you don't need to know that one for this subject. Some different gears that you might be interested to have a look at, with some explanations of advantages and disadvantages. Here's a table, different types of gears, with some features of the different types of gears and applications, and some comments regarding those, so you can have a look at those if you want to. We've got the advantages of non-synchronous and also disadvantages of non-synchronous belt drives. Here's an example of a non-synchronous belt drive, the V-belt inside a pedestal drill. When you're down in the workshop, you can maybe ask the lab staff to open up the pedestal drill and you can have a look. In this case, we don't need a precise angular alignment between the input and the output. We just need to transmit the rotation. So there can be some slipping, which may even be beneficial if we're trying to work too hard with our drill, or it gets stuck or something. So we have a slipping rather than things breaking. Synchronous belt drive example in a 3D printer. Okay, so this toothed belt here and tooth pulley drives the print head along these linear guides here. So in this application, we want to make sure that the print head is exactly where we think it is. Okay, so we can't have any slipping, or we're not going to get our 3D print model printed how we want it to be printed. And lastly, you should know by now from our understanding of gears that there's something not quite right here. Okay, so that's it, and I hope you have found that useful and valuable, and I'll catch you next time.